Quantum mechanics is the branch of physics that describes the known behavior of matter and energy at the atomic and subatomic scales. It deals mainly with the extremely small, like atomic and subatomic particles. It works on the macroscopic level as well, but with a few exceptions, such as superconductors and superfluids, the results are usually the same as classical mechanics. It is, however, at the subatomic level that the differences between classical and quantum mechanics become significant. Quantum effects are classes of phenomenon with no counterpart in classical mechanics. Some of them are quantization, the uncertainty principle, wave-particle duality, quantum tunneling, quantum entanglement, and quantum teleportation. Quantization is the situation where physical quantities like position, energy, and momentum can have only certain discrete values. For a particle free in empty space, these physical quantities are continuous, but a particle bound to an area of space can only have certain discrete values. The uncertainty principle basically states that there is a limit on the accuracy of simultaneous measurement of physical quantities, like a particle's position and momentum. As a result, the more accurately one measures a particle's position, the less accurately one can measure its momentum, and vice versa. Wave-particle duality is the tendency for light and matter to exhibit the properties of both waves and particles. It is a key concept of quantum mechanics. Put another way, light and matter sometimes act like particles, exhibiting properties like scattering. Other times they act like waves, exhibiting properties like interference and diffraction. Quantum tunneling is related to wave-particle duality, in that it results from the wave nature of a particle. It is the process by which a particle gets across a barrier that it cannot classically pass. Now, the probability of an individual particle getting through the barrier drops exponentially with the thickness of the barrier. However, with a large number of particles, some will get through. Quantum entanglement is the phenomenon in which the quantum states of two or more objects have to be described with reference to each other, even though the individual objects may be separated in space, so that a change in one object causes an instantaneous change in the others. Here is an illustration. Bob and Jane become quantum entangled. Bob and Jane then become separated. Tim comes along and kicks Bob, and Jane says, "Ouch." Quantum teleportation is the transporting of a quantum mechanical state between two locations by way of an entangled state and some classical information such as light. The need to use classical information eliminates this as a potential faster-than-light communication method. There are several different interpretations of quantum mechanics. One is called consistent histories. In this view, quantum mechanics simply predicts the probabilities of various alternative histories. Next is the Copenhagen interpretation, which says that the only thing that matters are the experimental results. Now, while this is currently the most popular interpretation, it is losing ground. Next, we have the transactional interpretation, which sees quantum mechanical waves as standing waves in space-time, constructively interfering where the particle is and destructively interfering every place else. Next, we have the Bohm interpretation. In this view, the waves guide the particle. Now, while it is totally deterministic, it requires a large number of hidden variables, which cannot be directly measured. Next, we have the many worlds interpretation, which sees the world as constantly splitting off into multiple universes in which every possible quantum event actually occurs. The next view simply posits that consciousness collapses quantum mechanical waves. Finally, we have general intelligent design, which postulates that quantum mechanical waves and their collapse are a result of intelligent agents that determine the states resulting from the wave's collapse. These intelligent agents could be actual intelligent beings or mechanisms programmed by an intelligent being. Quantization is the situation where physical quantities like position, energy, and momentum can only have certain discrete values. For a particle in free space, these physical quantities are continuous. But for a particle bound to an area of space, they can only have certain discrete values. The energy contained in a given frequency of electromagnetic waves is also quantized. That is, it always has the same value at the same frequency. The energy is found in discrete packets called photons. The quantization of electron energy within an atom explains much of their behavior, such as why atoms emit only discrete frequencies of light. This illustration shows an electron sitting in a low orbit within an atom. A photon comes along, which is absorbed by the electron jumping into a higher orbit. The electron then emits a photon of the same frequency, jumping back to the lower orbit. There are several natural units that were proposed by Max Planck. They are based on 5 universal physical constants: the gravitational constant, Planck's constant, the speed of light in a vacuum, the Coulomb constant, and Boltzmann's constant. Most of these natural units have no physical significance. However, 2 of them, Planck length and Planck time, are the smallest possible measurements of space-time, according to our current understanding of the laws of physics, specifically the uncertainty principle when applied to these scales, suggesting that space and time themselves may be quantized. The formula for Planck length shown here is the square root of Planck's constant times the gravitational constant divided by 2 pi and the speed of light cubed. Its value is 1.616252 times 10 to the negative 35 meters. This is the smallest measurement of length that has any meaning within the laws of physics as we understand them today. Here is the formula for Planck time. Planck time equals the square root of Planck's constant times the gravitational constant divided by 2 pi and the speed of light to the 5th power. Its value is 5.39124 times 10 to the negative 44 seconds. This is the amount of time that it takes a photon to cross a Planck length. It is the smallest measurement of time that has any meaning within the laws of physics as we understand them today. In conclusion, quantization requires physical quantities to have discrete values. It explains much of what goes on inside the atom. Finally, our current understanding of the laws of physics suggests that space and time are also quantized. The uncertainty principle is the principle of quantum mechanics that there is a limit on the accuracy of simultaneous measurement of physical quantities like a particle's position and momentum. The uncertainty principle was published by Werner Heisenberg in 1927. It is based on the fact that the light needed to observe a subatomic particle will disturb it, making measurements of it uncertain. The uncertainty principle is most commonly expressed as the change in x times the change in p is greater than or equal to h over 4 pi, where x is the particle's position, p is the particle's momentum, and h is Planck's constant, equal to 6.626 times 10 to the minus 34th joule seconds. Now, as you can see above, Planck's constant is too small for the uncertainty principle to show up in the macroscopic world. However, it is significant in the subatomic world. The result of this is that the more accurately one measures a particle's position, the less accurately one can measure its momentum, and vice versa. This is not the case just because the act of measurement disturbs the system, which it only does sometimes. It is related to wave-particle duality. The same uncertainty relationship applies to other quantities as well, such as energy and time. The uncertainty principle shows that there are limits to our ability to make measurements of the subatomic world. It shows that there are limits to our possible knowledge about the universe. Wave-particle duality is the tendency for light and matter to exhibit the properties of both waves and particles. This is a key concept of quantum mechanics. Scattering and diffraction are 2 ways that subatomic particles exhibit this dual nature. They sometimes act like particles by exhibiting properties like scattering, while at other times they act like waves exhibiting properties like interference and diffraction, such as the electron diffraction pattern shown here. 2 experimental examples of wave-particle duality are the photoelectric effect, in which photons of light eject electrons from a sheet of metal, just as interacting particles should behave, and the Davison-Germer experiment, where an electron beam is aimed at a nickel crystal. As you can see, the resulting scattering has peaks and valleys due to diffraction. The formula for the wavelength of a particle's wave is lambda equals h over p, where lambda is the wavelength, P is the particle's momentum, and h is Planck's constant, which is equal to 6.626 times 10 to the negative 34 joule seconds. The wave function of a particle is denoted by psi. The exact formula varies with the situation. The wave function is a complex number, and it is related to the probability of finding the particle at a given point in space. The probability density, which is the probability of finding a particle at a given point in space, is denoted by the absolute value of psi squared, or psi star times psi, where the complex number is denoted as phi equals a plus ib, and the complex conjugate phi star equals a minus ib. Over all of space, the probability density of a given particle equals 1. In conclusion, matter and energy behave as both particles and waves. Furthermore, the wave nature is related to the probability of finding a particle at a given location at a given time. Quantum tunneling is the process by which a particle gets across a barrier that it cannot classically pass. It is related to wave-particle duality in that it is a result of the wave nature of a particle. An important aspect of quantum tunneling is the fact that the probability of a given particle getting through a barrier drops exponentially with the thickness of that barrier. The main formula for quantum tunneling is psi of x equals psi of 0 times e to the minus k x power, where psi is the particle's wave function, e is the natural log base number, k is the particle's wave number inside the barrier, and x is the distance from the start of the barrier. The formula for a particle's wave number inside a barrier is k equals the square root of 4 pi m times e minus v divided by h, where m is the particle's mass, e is the particle's energy, v is the barrier's energy, and h is Planck's constant, which is equal to 6.626 times 10 to the negative 34th power joule seconds. When a wave comes in contact with a barrier, most of it bounces off. However, some of it passes through the barrier, but how much decays exponentially with the thickness of the barrier. As the amplitude of the wave increases, the amplitude of the wave on the opposite side of the barrier increases. As the barrier's thickness increases, the amplitude of the wave on the opposite side of the barrier decreases. As the wave energy increases and correspondingly the wavelength decreases, the amplitude of the wave on the opposite side of the barrier increases. If the wave energy is greater than that of the barrier, then nearly all of the wave passes through the barrier with a longer wavelength. For particles, tunneling means that while most of the particles still bounce off of the barrier, a few instantly get through. The shorter the barrier, the more particles get through. If the barrier is thicker, fewer get through. Increase the thickness of the barrier further, and even fewer get through. The slower the particles are moving, the fewer of them get through the barrier. Speed up the particles, and more of them get through the barrier. Speed up the particles some more, and even more of the particles get through the barrier. Speed up the particles such that their energy exceeds that of the barrier, then almost all of the particles get across the barrier, but at a slower speed. Quantum tunneling gets subatomic particles across barriers that they normally cannot get across. The number of particles that get across the barrier drops exponentially with the barrier's thickness. The number of particles that get across the barrier increases with the energy of the particles. Quantum tunneling is a purely quantum effect, in that it has no counterpart in classical mechanics. Quantum tunneling could theoretically occur on the macroscopic scale, but the odds are too small to ever see it actually happen. Quantum entanglement is a phenomenon in which the quantum states of two or more objects have to be described with reference to each other, even though the individual objects may be separated in space. The result is a correlation between the observable physical properties of the systems, such that a change in one object causes an instantaneous change in the other. In this illustration, we have two particles that start close together and become entangled. In this case, their colors are entangled. One is red and one is blue. They then separate and move apart. Along comes a photon that turns the red particle blue, and instantly the blue particle becomes red. As the second illustration, Bob and Jane become quantum entangled. They then separate and move apart. Tim walks up to Bob. Tim then hits Bob, and Jane says, "Ouch." It is generally thought that classical information cannot be sent faster than light by this means. One reason is that two particles need to be near each other to become entangled, except by means of an intermediate particle, which has to be near one particle and then the other. However, this would not prevent sending information faster than light in cases where the sender and the receiver were originally near each other and then separated, such as a spaceship that leaves Earth and then uses such a means for communications. Quantum entanglement is a purely quantum effect. It has no parallel in classical mechanics. The double slit experiment is based on the wave-particle duality of subatomic particles. As simple a concept as it is, it produces some of the most astonishing experimental results of quantum mechanics. This experiment stands at the heart of quantum weirdness because it is one of the strangest things in science. Shooting classical particles, that is, small balls of matter, at a screen with a single slit in it produces a simple spray of particles on the second screen behind it. When a wave passes through a single slit, it produces a similar pattern. That is, a bright spot in the center that dims as one moves away from the center. When you add a second slit to the first screen, classical particles would tend to form two sprays of particles on the second screen. When you add a second slit to the first screen, a wave forms a series of several light and dark stripes, as shown below. Shooting quantum particles, that is, subatomic particles, at a screen with a single slit in it produces a simple spray of particles on the second screen behind it. So far, so good. This result is actually consistent with both waves and particles. Now, this is where it starts getting strange. Shooting quantum particles at a screen with two slits in it, one would expect them to form two sprays of particles on the second screen. However, when one actually shoots quantum particles at a screen with two slits in it, like a wave, quantum particles form a series of several light and dark strips. This shows the wave nature of quantum particles. As strange as this is, the quantum world gets even stranger. One possibility that was considered is that the quantum particles are somehow interacting with each other to form the series of several light and dark strips. The solution was to shoot the particles one at a time so that they cannot interact. Here are the results of a double-slit experiment showing the buildup of an interference pattern of 100 single electrons. Here is the result of a double-slit experiment showing the buildup of an interference pattern of 3,000 single electrons. Here are the results of a double-slit experiment showing the buildup of an interference pattern of 20,000 individual electrons. Here are the results of a double-slit experiment showing the buildup of an interference pattern of 700,000 individual electrons. Note that the electrons still form an interference pattern, even when shot one at a time. This shows that the wave nature of subatomic particles is inherent in each particle. These results actually seem to require each electron to go through both slits at the same time. However, quantum mechanical strangeness still gets even stranger. The notion of one particle going through both slits at the same time is so anti-intuitive that physicists had to look to see which slit each particle is actually going through. So to look, experimenters put detectors by the slit so as to look to see which slit each particle actually went through. The results were that the subatomic particles formed a spray line behind each slit, just like classical particles would. This suggested the electrons somehow knew that they were being watched. And this is not the end of the strangeness, because it's about to get even stranger. Suspecting the detectors were causing the difference, the experimenters turned off the recorder while leaving the detectors on. However, this time they got the interference pattern. The fact was that the subatomic particles only produced the double line when the information about them was actually being recorded. So it is the conscious act of observing that affects the experiment, and not the measuring devices themselves. So what is really happening is that when a subatomic particle is not being observed, it behaves like a wave, and can actually go through both slits at the same time. The properties of this wave are determined by the particle's wave function. On the other hand, when a subatomic particle is being observed, the wave function collapses and it behaves like a particle and can only go through one slit at a time. In general, the idea is that the wave function represents multiple possibilities. When an observer is added, the wave function collapses into one of those possibilities. Now, exactly what causes this depends largely on the particular interpretation of quantum mechanics being used. Ultimately, each interpretation is a different view of reality itself. One thing this does show is that consciousness is a fundamental part of reality. This is not New Age thought, but with the observation of subatomic particles is actually final. It is also consistent with the biblical view of God as creator, since the universe would be a result of his consciousness.